And we're live. We are live.
Hello, good morning, everyone. Well, at some places it might be evening or not. So anyway, welcome to the machine learning for software engineering. And today we have very distinguished panelist, Miltos Almanis from Microsoft Research, and Michael Pradel from University of Stuttgart, and Vincent Hellendorf from UC Davis, soon joining CME. So I will start with the panelists introduce himself and also talk a little bit about the work they are doing right now. So how about we start with Miltos?
Sure. Hi, everyone. My name is Miltos. I'm a researcher at Microsoft Research in Cambridge, the UK Cambridge. My work is in machine learning, deep learning, applied for software engineering, and specifically I'm looking for software engineering tools. My background is mostly coming from a deep learning and machine learning background, and my essentially hope for my research is to gradually try to use machine learning to get better tools to software engineers. At least in Microsoft, we have Visual Studio Code, and GitHub. We have been collaborating with quite a few of those products and product groups, and many interesting applications that come up either in the IDE or in a website in a community like GitHub. More recently, I have been focusing on graph neural networks and a specific flavor, let's say, of deep neural networks that can process as input graphs and can output graphs. And from that, we've been looking at things like how can we find bugs that are not necessarily traditionally found with static analysis, but also other tools like code completion and code search that we've been kind of trying to combine the natural language, which is ambiguous because it's natural language, with source code, and trying to combine these two modalities to get better tools. I guess that's all I have. Can move on.
Okay, thank you, Miltos. Then Michael, can you introduce yourself?
Sure. First of all, thanks for having me. It's a pleasure to be here, whatever here means in this virtual world. So I'm a professor at University of Stuttgart, where I'm working on program analysis, and that has also been the focus of my research for the past, 10 years or so. And a couple of years ago, I realized that there's this powerful technique called machine learning, and in particular deep learning, that can actually improve program analysis quite a bit. So since a couple of years, I'm focusing a lot on learning program analyses and learning developer tools instead of just coding them the traditional way that we've been coding them for the past, I don't know how many decades. So I'm in particular interested in a couple of problems like bug detection or type prediction. The piece of work that is maybe most known in that space from me is a tool called DeepBugs, which has been one of the first to find bugs using machine learning. Similar to some other approaches that have been proposed in that space in the last few years, it's not only using the information that program analysis traditionally looks at, but also natural language information. So essentially, it finds bugs where the variable names and other natural language hints tell you that the code is wrong because you shouldn't combine these two names with each other, for example. Last year I've been on a sabbatical at Facebook, where I tried to apply some of these ideas we've been working on in practice, and one outcome of this was a nice tool on learning-based type prediction called Typewriter, which is now used by some developers in practice. And yeah, it's always nice to see that academic work can also actually be used in practice.
Thanks, Michael. And Vincent, can you introduce yourself?
Yeah, hi, I'm Vincent Hellendorn. I'm currently wrapping up a PhD at UC Davis and moving to Pittsburgh this summer, where I'm starting at CMU. And so for me, it was, I'm mostly a software engineer originally, but then early in my PhD, it became pretty clear that deep learning was here to stay and that it had some really powerful applications in software engineering. And so my research focuses mostly on both applications and sort of modeling improvements of deep learning, but with the express goal of kind of trying to bridge the gap between what we know specifically about software engineering and what these models can and do and code in practice. And so some of my work is focused on like, how are these models falling short of some vocabulary issues, and then kind of demonstrating that. And some of that has actually been solved since then with newer models. Actually, one of them by Miltus's former advisor to recently. And then other work has focused on sort of like, can we bring these models closer to our intuition about source code? So I published that at iClear this year. And so that's for me, is all my work is kind of, it comes from this perspective of what do we know about software engineering, and can we bring that into these models about deep learning, and vice versa, what do these models bring that we can maybe sort of fit to the context in software engineering that we have to kind of make them work better than the standard out-of-the-box applications.
Thank you, Vincent. So we start having a couple of questions. The first question is from Alexander, and he asked, how do the panelists see our role or balance of academic and industrial research done in this field? Is it different from other fields or SE in general? Is it changing over time? I think all of you should answer this question, especially because, I mean, Miltosh, you are from industry, and Vincent and Michael, you both are from academia, so you guys should have different opinions. So why don't Vincent start this time?
All right, so there were a couple of components to that question. This is actually a topic I've recently become interested in, is sort of the balance and often also the imbalance between industry and academia. One of the things that is most interesting to me personally is the imbalance in resources. I was at Google last year, and then it was pretty common to run 1,000 different GPUs at the same time to do some kind of search. And I thought that there's probably a trend over time where industry is pulling away from academia in terms of the sheer kind of resources they have available. And for deep learning, that's not just about like, I can get 1 extra percentage point, but there's actually differences in sort of the fundamental way these models perform when you have this capacity and when you can build these very large models or do these very large searches. Now, I don't think you can easily close that gap in any realistic way, right? Funding is always going to be bigger in industry. So the role that I see for academia is kind of looking more at what are innovations or sort of like fundamental problems that we see with these models or with the way they're being applied. And I think those kind of innovations and the fundamental issues that we find will probably extend also to the much bigger things being used in industry. So I see our role more as sort of like maybe kind of talking about validity, external and internal validity, and finding these issues that industry might not necessarily be looking at per se. Whether that's different from other fields, I don't know, but it's definitely changing as this gap grows between industry and academia. So that is definitely happening.
Thanks, Vincent. Miltosh?
Yeah, so I think there is something special about machine learning because it's, at least deep learning has been taken over by the industry and be led by the industry in the last 6-8 years, much more than other like subfields of computer science. So in that sense, obviously machine learning is being driven a lot by industry people at this point. And the main advantage that companies have is a lot of data. and that might be a problem in academia. On the other hand, if we look at the progress that the deep learning field has been making, we are going one direction that seems to be going really strong is relatively simple models with tons and tons of data, like transformers or things like BERT, you might have heard, or things like that. These are places, and this kind of research can happen more easily in industry rather than academia. But at the same time, I think that the academia has this opportunity to get into looking into more crazy ideas. In many cases, especially product groups, not necessarily research departments in big companies, have to like get a product out soon. They have to fix something that is very immediate. Whereas academia can take the time to think ahead and try to look at these crazy ideas, if you wish, that might not work, but they have, let's say, the absolute imperative to kind of explore everything without having to ship something tomorrow. So I think the role will be that temporarily we're seeing industry having the lead in deep learning, but we need to have a diversity in exploration of ideas, and I think that's what academia can bring into the game.
Michael, what do you think?
So I would take a pretty optimistic look on this balance or imbalance, actually, because in contrast to a lot of other subfields of software engineering, there is a bit more of a balance. So there's a lot of interest from industry in this area. There's also some interest in other subfields of software engineering, but at least in my perception, there's a higher ratio of industry people that care about ML for SE than that care about SE in general. Now, this may be a controversial statement, but at least that's my personal perception. So, and I think this is great, because that shows that this whole field is valued, and I think as academics we should actually be thankful that the industry also cares about this, and we are not just researching in our ivory towers. One problem that comes with this, and that's something that Mildred also mentioned briefly, is data. So in some large companies, there are really good data sets that would be wonderful to have in academic research, but it's sometimes not so easy to get access to it. So what would be great is if in the future we would find some ways of sharing some of this data in some way. I mean, it's inherently difficult to do this because of many reasons, IP and privacy and so on. But if basically every shared data set that comes from industry about development practice is valuable, and researchers will jump on it and use it. So basically a shout out to people in industry: if you have some data to share, please share.
Great, thanks. Quick follow-up questions came from Diomedes. And here I am posting, it's basically, I mean, given that industry definitely have more resource and data, what is the scope of academic research involved? I mean, basically what academia can offer. Michael, what do you think? You are in academia in most, I mean, among, I mean, quite.
At least most of my life I'm in academia, yeah.
Yes, yeah.
I mean, it's true that there are some models that require a lot of computational resources, and that it's practically impossible for the average academic to ever train such a model. That is a fact. At the same time, I think that's only true for a small percentage of all models that are proposed right now. So there are a lot of things you can do in academia without really needing access to these huge computing resources, but basically buying 1 or 2 servers with powerful GPUs is enough, and that's in the budget of almost every academic I know. So I don't really see this as a huge problem, at least not at the moment.
Mm-hmm. Others, do you want to add anything?
I think I would like to add that it's definitely true that companies have data. If we look at user-facing data, like what people search, for example, or things like that. But what we see is, like, if you take big companies, there is a lot of data about code data that cannot generalize beyond the company within, like the APIs of the internal tools, toolkits, libraries that they're using. And I think what we're seeing in this general field of machine learning for software engineering is that, like, there are not that many operating systems, database systems, and trying to find these models that can generalize with fewer data, and is a very big problem, which is both important, of course, for industry, but also somewhere where academia can find it's where can definitely contribute, and can also find ways to resolve essentially the problem of not having data by turning this problem into a research question, which a lot of people have, and it's not necessarily code specific, but it's still something. How do we get all of GitHub, all of the open source projects, and try to generalize and learn from these things, despite these things having very, very different domains? So I don't think that's necessarily the resources as a constraint, but it's more like as an interesting opportunity of seeing these things, that it's different to create tools for internally for Microsoft, Google, Facebook. It's different to create tools for developers out in open source. We're going to be working on a very different stacks and a variety of things. And I think that's the most interesting case in any way. So there is certainly a scope for academic research in that domain, and there is scope for the research for everyone in that part.
Mm-hmm. Vincent?
Yeah, I would agree. I think Miltos, that's a good point. Is that for one, there is a lot of data on our side, right? GitHub has been just this incredible resource, and it's growing vastly. And I think I also agree with Michael that, like, the times I've been able to work with industry and use, sort of interact with their data and resources have been great. And that seems to be a thing to stay. There's a lot of attention and demands there. So I think that's a positive thing. And I think also there's something about scarcity that brings innovations, right? So some of the more interesting papers recently have been on meta learning, or coming up with sort of compressed language models in our field. I think that's kind of an interesting way to turn what is very much a resource problem into a research opportunity. So I think there's definitely a lot of room actually for academic experimentation here, and maybe in part due to this gap, but also just in part because there's many other resources that can be used as sort of proxies for what industry might be seeing.
Right. Yeah. I mean, I also kind of agree, and I think for as an academic people, I mean, we also are not bound to company requirements, so you can experiment with more, I mean, different applications. So that is also a good point to add. I mean, and kind of you can go in different direction if you want. So, okay, let's move on to some more, a little bit, there are a lot of questions coming, which is good. So Sarah asked, for program analysis, when do you resort to a ML approach, when you can have a more precise technique to analyze program, like find bugs, properties, etc.? In other words, in your experience, when did ML help with program analysis, and when did it do more harm than good? So let me. So Vincent, do you want to go first?
Sure. Yeah, I can take a sort of an initial stab at an answer. I think there's two parts to this for me. The first half is we don't quite know. We're seeing a lot of people, either papers or people talking sort of about research, talking about ideas on how can we merge these two domains. And I think that is because it seems like there is actually a lot of room for machine learning here in terms of this natural channel where it's like, there might be lots and lots of statements I can soundly make about the code, but it sure looks like the following is true. Like this seems like a bug, or this seems like it's definitely a numerical type based on how it's used, even though, no type check on earth can soundly say this is an integer just because of dependencies, or because of the usage could also be a string, right? And so we're seeing applications like that where machine learning adds this very rich alternative channel of explanation to code And it seems like, a lot of sort of traditional program analysis tools, and, others are more well-versed in those than I am, but they're kind of more constrained by what can you soundly or precisely or completely infer. And so there's some interplay between those two. Now, how exactly you leverage that interplay kind of depends on the task. And I don't think we've seen sort of a very comprehensive approach that solves that. I did a paper on type inference, and there the idea was just we make type predictions and then we run them against the compiler, and the compiler can say, well, this looks, at least it's not invalid, and that's all it can say. So now you have a soundness-like guarantee, but you also can infer many more types than sort of traditional tools could, because you're kind of learning them organically from names and interactions. So that is one example, but that of course doesn't work for many other tasks where you maybe don't have that oracle that can say, well, this is not incorrect, like bug detection. So I think there's a lot of, so far I've seen it sort of very specific, like here's a task. But I think we'd like to see maybe a bigger framework of how can these two communicate. But there is a lot of room for communication, I would say.
Mm-hmm. Any other one want to take this question?
Yeah, I can try to say a few words. So I think there are basically three conditions that I look for when I'm thinking about, is this a good problem to solve with ML in the program analysis space? One is, that's the obvious one, is there data available? I mean, because as we already mentioned, you obviously need a lot of data, and either you have this data in some form or there's some way how you can generate the data. So there obviously is a lot of code, but then if you look for other properties of code, or maybe things that go beyond code, it's not always that obvious how you could get the data. So that's one dimension. The other is about the sort of fuzziness of the inputs. So in source code itself has clearly defined semantics, at least in most languages. But then there are a lot of things we do not know about the code, and if there's a lot of things we do not know about the code, then machine learning is usually very helpful. So for example, by considering natural language information in code, we are considering an input that is pretty fuzzy, because I mean, what does it mean that a variable is called list or IND, right? It's not really well defined, but still machine learning can see some patterns in there and then learn from that. And then the third dimension is about how well we can judge whether the output of an analysis is actually what we want to have. So if there's a specification and you basically just have to try out all different ways to satisfy that specification, then maybe a traditional analysis approach is a good idea, where you just enumerate these possible solutions and then check if this is correct. But in many applications, you do not have this precise criterion that tells you whether the output of your tool is actually correct. So for bug detection, for example, unless you have a perfect test suite, you don't really know, right? Someone has to look at it and then judge. And there are many other problems like this, like estimating the riskiness of a code commit, for example. There's not really a ground truth where you could say, okay, this is exactly what I want to get. And that's also, so if you have this fuzziness also on the output side, then machine learning usually also is a good choice.
Okay, I mean, given that we have so many questions coming, I think there might not be time for each of us. So let me present the next question. So the next question is, any insights on how to present these recommendations to developers, given that they are just harder to explain when compared to the regular analysis? How will you present? So basically, explainability question. Maybe Miltosh, I mean, if you want, I mean.
Yeah, sure. And I don't have a lot of things to say here. I think it's a really good research question. I don't think that it has been explored enough. The user experience, the way we communicate uncertainty to the user about some specific decision is important. Making sure when to suggest and when not to suggest is important. It's hard in some cases to find this sweet spot, and I think it really matters. It's a per application kind of thing. So if you look like at the code completion and IntelliCode, what's currently in Visual Studio and Visual Studio Code, the machine learning based code completion works reasonably well, in the sense that you can rank in the top list, you can rank the most probable suggestions. Now, if you want to say to a developer, hey, this might be a bug, for example, this is more tricky. The developer might get defensive, or they might find a false positive, which they are bound to find because it's machine learning, and they might completely tune off these kind of errors. So yeah, the high-level answer is a lot more research is needed. I don't think that I at least have a clear answer on this.
So I think the question was more like, say, when a machine learning model says that this is a bug, there is no explainability, right? Like why it thinks it is a bug, and that kind of may make the developer less confident about that prediction. And I mean, are you guys thinking, I mean, this is question to all of you. Are you guys thinking like how to address this problem? Like,
yeah, so I think it's a very important problem, and yes, I'm thinking about how to address it. So for bug detection in particular, what I think is pretty useful is if you do not just tell the developer, hey, this code looks wrong, but also suggest how to make it correct. So if you say, oh, if you change the statement just like this, then I think it's better. And then a developer can basically just look at these two options and compare them and say, oh yeah, you're right. Or maybe say, no, you're not right, that's a false positive. So just predicting that something is buggy is certainly not helpful, but if you give an alternative, it's good. And then maybe the other answer that is also specific to bug detection, because that's what I've been working on quite a bit, is if it's not just buggy or not buggy, but if it can say it's buggy because of this particular kind of bug, that's very helpful, because then it's not just a binary warning, but you give some indication and say, hey, I think this is this particular bug pattern. Please have a look.
okay, that sounds good. So let me go to the next question. One came from Alexander Serprenik, that fairness is often seen as Achilles heel of machine learning. Do you see any fairness related concerns in application of ML to SE?
Yeah, I've actually, I've sort of recently started talking to a wider range of people to see if they're starting to see that, because I think we've kind of initially been, I would say, been immune to that, because all we've been doing is taking Java and sort of running it through a, through some machine learning model, and there's not that much. I mean, there is actual diversity of language encoded in Java too, but in general, most Java is sort of written in English, and you don't necessarily notice that. But I think that is shifting. I think we're seeing more and more machine learners that are doing kind of more comprehensive tasks, where they're looking not so much at just here's code, say a thing, but maybe here's code and here's the comment from a previous user, respond to that comment, or sort of like try to determine whether they're correct about this, or maybe, like have it in a code review in a feedback loop. And that is all still very futuristic. I don't think anyone has necessarily done that, but enough people are sort of working on this that I know that I think that is going to be more immediate. And we know for a fact that on GitHub, there's plenty of issues with fairness and bias. Danae Ford from Microsoft Research in Redmond has done quite a bit of work showing that there is definitely, people kind of their judgment very quickly skews the moment they see a profile picture or kind of language that doesn't reflect their own. I think that was also in there. So I think we're going to see this, and we're going to see it quite a bit, and we'll need to work on that. But that is more the moment you kind of bring in not just the natural channel from identifiers, but rather from like actual human communication, what comments are being written, how are people talking, kind of sentiment and tone, those kind of factors.
I can just quickly add one thought here. So in addition to what you said, I think there's another level of potential unfairness, which is basically in the amount of data available about particular languages, libraries, frameworks, coding styles, and so on, right? So it's all these models will work much better for languages that are popular, and there is a bias towards popular libraries, for example, because there's a lot of code that uses them, and if the tools are better for these libraries, then of course more people will use them. So there's this effect that focuses us more and more on what's popular. Yeah.
Right. Miltush, do you want to comment anything?
Nothing more than that. I think fairness is indeed a problem. I think it's application dependent. Machine learning has various definitions and various ways to try to train models that are more fair. But I don't see an overarching issue across all possible machine learning for code applications. But each application should be looked specifically, and we should all, of course, try to make sure that any fairness issues are addressed. And especially when you start involving people, that can happen. You can say your style, or because of your style, your code style, your code is wrong, or like our tool is not useful, things like that. But I don't think we have observed this in the practice. As these tools proliferate, that might be the case, but we'll have to see, I think, in the future where these problems appear, and then we'll find ways to attack them.
Thanks. So the next question is from Oscar. It's kind of a generic question. He said, so what do you think are the limits of applying machine learning to SE? What is the impact of SE research and practice of blindly applying ML to SE, where ML to SE in many cases is a matter of using large data? Sometimes I feel this is the case because the great popularity of ML and DL.
I can try starting with this one. So I think there is a big gap between designing deep learning and machine learning models that are specific to software engineering applications and applying out of the box deep learning models to some software engineering problem. And on one hand, it's obvious that people will keep trying to do that, and given a promise that machine learning has shown in other fields. I think the limitations are, or at least maybe I'm biased from my research perspective, are on the machine learning side of things. We don't necessarily have the tools to combine these different forms of data, the formal constraints that code brings into one overarching framework. So this is certainly one of the limitations that is coming up again and again. And at the same time, what it's commonly had to happen in many cases that you try to squash your data into something that an existing machine learning component accepts. And this might give suboptimal results. And it'd be great for the software engineering community to get all the domain knowledge that we all have, and try to help the machine learning people to design and to specialize all these models. I think that answers the question. I guess maybe it should also be said here that machine learning is not, doesn't solve all problems, right? There are many cases where machine learning isn't the right answer, or at least not a deep learning full neural network is the right answer, but maybe a simple decision tree or maybe a very simple model is the solution. So I guess the impact here to software engineering should be that that during the review process, we should all try to have simple baselines to make sure that we're not over-engineering something, and instead this powerful machinery that deep learning machinery, for example, is actually necessary for this problem, given this data, given the studied setting.
Mm-hmm. Thanks, Miltosh. Any other thought, guys?
Yeah, I just want to sort of chime into that. I think Miltosh raised a really good point, which I would say this idea of blindly applying ML, I think it's kind of run its course. I certainly still see a lot of papers being archived that kind of like take a machine learner from another field and sort of apply it and say it looks better, the results are better. But I think that was probably most useful 3 or 4 years ago. Mm-hmm. Where now the papers that I read that I think are really impactful are people who are taking maybe an idea from another field, but kind of really tailoring it to software engineering and bringing in our, like Milto said, our domain knowledge, and making sure that we're actually, both internal and external validity, right? Is the model doing the right thing for software engineering? And is it actually solving something that matters? And that work, I think, is super important. And we need more work like that. So actually the role, there is no such thing as blindly applying these things. I'm seeing it still happen, but I don't think it's much useful anymore. We need quite the opposite. We need more software engineering experts to help us out and kind of help us fit these things to the audience. As for the limits, I would also agree with Miltosh that it doesn't. Oh, sorry.
No, sorry for interrupting you.
Okay, I would say there's definitely a lot of things. Machine learning is very much a tool, right? It sort of automates the parts of our brain that maybe don't do any super exciting processing of code, right? Sort of the code completion, like we're just typing, the machine learner can take over some of that work, or simple bugs. We're so busy, we might not notice them. But the limits there are, until we get to AI complete are way far out, right? Most of the coding that I do is more higher level strategizing and planning, and that is totally out of the scope of machine learning for probably many years.
So a very related question came. I am reading it related to the difference in resources. What is the path forward for ML on code? Is it the future more like GPT-2, 3, or is there still room for new specialized model architecture for code? And related to what about representations, token level, many GPUs seems hard to beat, etc. So I think it is kind of a very follow-up question on what we are discussing right now. So basically, whether we need new kind of model architecture, etc. Michael, do you want to take that one?
Yeah, sure. So So I don't think just taking a model that is good on some other in some other domain will work very well for code. And the models that we see that work pretty well are usually targeted to the specific problem, or at least to code. So the graph neural network work that Miltos and friends are doing is a good example. It's a model that is, it's a model that has been proposed somewhere else, but then it's specialized to the domain of code by basically using all the existing compiler knowledge that we have to create nice graphs, and then train the model on these graphs. And I think there's still room for more work along these lines, where we have good representations of code that may come from compilers or maybe just new, and then models that fit these representations.
Mm-hmm. So another very popular questions, and I think it's quite relevant, from Georgius. Lots of research is currently around 4 or 5 topics like type prediction, bug prediction, etc., that were more or less specified by the people in this panel. So what would be the next 99 problems to be tackled by ML4AC?
I wanted to. I specifically added the heart in the Slack, and I think this is obviously a very interesting question, right? The main issue that we're seeing here is the question of data availability, or like, what do we optimize in order to get something of a target application? And in many of these cases, we see ways of finding automated metrics that measure in some form the performance of this kind of the models. Like, what is the accuracy of predicting the type? How well do we predict the next token in code completion? Where do we find the bugs? The majority of interesting software engineering problems don't necessarily have this clear-cut metric, and I think this is a very interesting software engineering problem. So I'm going to give a kind of a non-answer in that sense, which is, if we look how NLP handled things in the early 90s, probably earlier, if we were to say, how do you evaluate a translation system? How do you evaluate something that summarizes text? There was no previously commonly accepted answer on that. And then the community through user studies started finding metrics, finding like the blue score, maybe you'll have heard, or the rouge score, ways to measure in an automated and scalable way how good a translation was or how good a summarization was. So I think this is the opportunity for the software engineering researchers to find these metrics that correlate well with what the developers want to see. And once we find these tasks that we have these proxy metrics, they're obviously imperfect, then I think this is when the machine learning models will start following. We will have a way, an objective to start optimizing. And yes, if you take translation, for example, the blue score was correlated for a long time with translation quality. And as we got better and better, the performance, like the correlation of how humans judge translation quality versus the blue score correlates a bit less. But we need these automated metrics that can scale up to what modern machine learning methods need, essentially an objective and lots of data where we can measure to which extent a machine learning model is good. So my kind of non-answer is if and where we can find these metrics and kind of decouple the problem of a user study of how well some system works with how a given method works. This is where I believe that the next generation of machine learning for software engineering methods will appear.
Do you guys also drive by the company requirement? Like say Microsoft wants something for say bug prediction or program fixing. Do you have any, does that kind of requirement drive the machine learning models?
This would drive it if this implies that if a company wants to solve a problem, they would go out, collect data, ask human taters, get metrics, get data sets that evaluate on the target task. So this is one way of thinking. If there's a pool kind of request of someone high up, we need to solve this problem, then you get to the money flows and you get all these extra resources you need to build this. Commonly, you also get the other way around, right? Which is you need to prove into some form have some promising results about some application, and then you go and say, this kind of works, let's try to push it to the last mile, which is always the gap between research and having it in a product. So both things may work and can work and have worked in various fields. There is no specific way I see at least happening across the industry.
Mm-hmm. Any other thought?
Yeah, I just want to add a little bit to Miltush's answer, which is I definitely agree that we need sort of these better benchmarks and metrics to kind of work towards to better imitate real development. But maybe as a sort of a more sort of short term, like if you're talking about what is next, I think a lot of the both the trend in this conversation and a lot of the things I do as a developer in my everyday life, the common pattern between those two is there is no real, very concrete, like immediate reward or sort of a clear function that says this is the next thing to do, right? So if I'm doing a code review or if I'm writing a test suite, there is no metric that says this is the right test suite, everything else is bad, So all the 4 to 5 tasks that you mentioned that we've seen so far are kind of the ones that are the loss is very obvious, right? Loss is integral to machine learning. And the loss was just, the next token or pick the right bug, don't do anything else. There's nothing hard. And I think the same in computational linguistics and even to some extent computer vision is we're seeing a shift away from tasks that are so obvious, like this is a photo, tell me what's on it. And more towards things where it's like, it's not so obvious how to assess the quality of this, right? Like if I'm playing a chess game, there is a goal all the way at the end, which is to win, but any intermediate move doesn't necessarily have a quality goal. And so reinforcement learning and various other sort of like, maybe like one-shot approaches can kind of give you, and there's a whole literature on this, can give you that kind of, that guidance to get to a good solution that is not necessarily the right solution. And so we'll see more work like that. So test case generation is definitely one like that for me. I think code review is also like that. But it will require some innovations in how can you guide a machine learner without necessarily having the right answer that it needs to generate exactly, or else, you know. So reinforcement learning, I would say, is definitely something to look into in general.
Mhm.
Yeah, I can also add two quick thoughts here. So one is maybe a reason why we see so many papers that focus on a very small set of problems. And I think that is that in machine learning, at least in machine learning research that is not on code specifically, people like to focus on a few problems. Basically, the way it works often in machine learning is someone puts out a data set, and then you have dozens of papers that try to be 1 or 2% better on that data set. And a little bit of this is also happening in machine learning for software engineering. Basically, if someone has started to look at the problem and there's a baseline that people can compare with, yeah, then we have a lot more papers. And that doesn't necessarily mean that the problem is that important. It's just, it's easy to do this work. That doesn't mean that the work is bad, but it's basically a reason why we see focus on a few problems for now. And then maybe a little bit more forward-looking. So I can't really list 99 problems now, but maybe an area where I see that more research is needed, and this is basically learning on runtime information. So a lot of the machine learning on code work is on static code, so it looks at source code as the data. But there's relatively little work on using runtime information, like anything you could get from a dynamic analysis, and basically do learning-based dynamic analysis. There are a few papers, but compared to the whole literature, it's definitely a small minority right now.
Okay, a very kind of, I would say, related question came from Abram Hindle. And the question is, what are your thoughts on the challenges of deploying SE4 ML solutions as SE tools that people will actually use?
So just to clarify, is the question really about SE for ML or about ML for SE?
I mean, basically the techniques we are discussing, SE for ML.
No, but we're discussing ML for SE, right?
But yeah, I think, I mean, that's maybe typo, I don't know. Let's stick to ML for SE for now.
Because there was another session, I think on Monday, on SE for ML.
That is true, yes.
They are probably in a better position to answer the question as typed in the Slack channel.
Yeah, for now, let's stick to ML for SE. And what are the challenges of using these solutions as a real life tool?
I can say what I've seen from my experience, at least within Microsoft, and first of all, there is a good question about the cost of these things. Usually, the one important question, especially for deep learning techniques, is the cost of supporting a service, which means developers, which means product managers, to support a specific feature for is not trivial. So the biggest problem I see here is finding this value which is useful for developers. The second part is it depends on the actual tool. And in many cases, the problems are if we want to add a small or big or huge neural network to every developer's machine, that's not always possible. We need to be careful about how we consume the memory, how fast or slow a method is, and all these kind of things. There are tons of problems, and that's probably a whole other field about how do we deploy machine learning, like deep neural networks, across different devices, across different architectures, across from Windows to Linux to macOS. So these are the two big things that are like the very practical, the very immediate things. And the third thing, which also comes back, is the user experience. We need to surface these outputs of these models in a way that communicates that this is not the absolute truth, but it's a probabilistic decision that some machine learning model made. We don't want to interrupt you. We don't want to have another clippy, but we want to do something which is useful, and it's useful at this point. That's much really.
Any other thoughts?
Yeah, maybe one additional challenge I see is how to adapt a learned model to a specific user and to the context in which that user is working. So what we currently, I mean, what we typically do in papers is we have some data set and then have some holdout part of this data set and evaluate on this holdout part, but the distribution of the entire data set is more or less the same. So it's maybe all from the same big project or maybe from the same kind of projects. But in practice, different organizations and different teams in organizations have different coding styles, use different libraries, and basically need different models. So one challenge is how to basically adapt the model to a specific team or to a specific user, maybe using some kind of retraining techniques. And yeah, so I haven't seen a lot of work in this direction yet.
Okay, so let's move on to the next question. This is from Vadim. It's how far do you think we are from solving certain problems with end-to-end ML-driven code generation? So what are the main obstacles on the way to do that? I think, so basically the question is probably how ML can be helpful for end-to-end code generation.
Yeah, I can try to give an answer here. So I think we're basically as far as we are in non-learning based program synthesis, which means it maybe works for some small examples, but it's not really ready for prime time. And I think the reason is the same for traditional and learning-based approaches. We need some way to encode what kind of program should actually be generated. And that's the hard part, because if you would be able to completely describe what a program or piece of code is supposed to do, then essentially you would have written the program, right?
Exactly.
So it's so, yeah. And that's the same problem no matter whether you learn how to generate the code or use some more traditional synthesis technique.
Do you think here, I mean, a hybrid approach, like some learning based and then some more traditional thing may be helpful?
I think I mean, probably it's better than each of them on their own, but at the same time, it doesn't solve this fundamental problem that we need a description of what the code is supposed to do. And this description by itself is often as complex, or at least also very complex as the code that we want to generate.
Right.
So I mean, I think my provocative statement here would be, I don't think we will in the foreseeable future be able to generate large amounts of code automatically, neither with learning-based techniques nor with traditional synthesis techniques.
Mm-hmm. Any other thoughts, comments?
Yeah, I think that's a good question. We should maybe first have an empirical study as a field that just says, if I throw a programmer in the following environment with maybe one comment or some context and nothing else, could they write the correct implementation, right? Because ultimately programmers are oracles. If they couldn't do it, then there's no reason for us to assume that machine learning is somehow magically better, right? If anything, it's almost always worse. So I think that's definitely a big part. The other thing I should say is, like, as far as current program synthesis goes, it is good for certain things, right? We're seeing cases where it can translate a comment to a line of Python, for instance. Debatably whether that's useful, but it's pretty good at that. But one of the obstacles we're seeing to kind of going to bigger programs is that a lot of the code right now is being generated autoregressively. Either you sort of expand an AST from left to right, or you just write every next token. And that doesn't seem to scale to these like very large text generations. I mean, it can, right? GPT-3 does a decent job, but code has these very rigid constraints that you must match parentheses and whatnot. And so I think one of the fields that is interesting to us is this idea of like non-autoregressive generation. Either not having an explicit loss that says generate the next thing now, or using reinforcement learning, or just more general approaches that kind of fill in the blanks over time. We're seeing a few papers like that are kind of like you start with something and then you correct it incrementally, and I think that is very interesting.
Mm-hmm. some problems can be solved in both ML and non-ML ways. When should we apply ML techniques?
I think we had this question earlier, right? Or at least the very
Yes, I think, I mean, in various ways, I mean, just some, summarization of this, any?
I would say for this question specifically, don't apply ML if you don't need it. I think, unless you're solving it in some way better with ML or with a hybrid, I don't see it. I would personally argue to use it. No.
So, okay, let's move on to the next question from Abram Hindle. Code is really strange because of its ability to generate new novel vocabulary. Much of DL literature in AC caps vocab size to 30K or less. Can you talk about how researchers of the future can address our curse of novel and evolving vocabulary? I think we all face this problem, so yeah. Who wants to go first?
Yeah, I can. I mean, I can say a few things. So there have been a few recent attempts to address this problem. Things like byte pair encoding or the n-gram-based approach that fast text is using, or contextual embeddings, and they all seem to work pretty well. So I'm not sure that. I mean, yeah. So I don't want to say it's a solved problem, but I don't see it as the main open challenge, actually, because I think there have been a couple of really good approaches.
So I think it also depends on the task you are modeling.
Sure. But I mean, if what you are reasoning about is code, then you somehow need to represent the code, and at least the
right. But say, for example, you are working on a program repair, and your next version introduces lots of new vocabulary. Then somehow the model should know about those new vocabularies, right? And if we don't know that, then that is a problem. Now, how to solve it? I mean, that's a different kind of discussion.
All right. Okay. Yeah. I think what you're saying is if the unknown vocabulary is on the output side of what the model should predict, then it's more tricky. And that's true. There hasn't been so much work. I mean, one example that comes to my mind is Milton's typilus type prediction work, where they have this type space, and instead of predicting it, that this is the type, they say, oh, it's here in the type space, and then you just look what types are close to this point in the type space and say, hey, that's the type. I think that's a pretty neat idea, and this could probably be also applied in other scenarios where you have unknown vocabulary on the output side.
I also think it's just a domain issue. It's like, how do we take a tool that has been trained, let's say, on databases and can now predict something on operating systems? And that's the same problem as the evolution in software. Like, we introduce a new jargon. On the other hand, as we humans introduce this jargon, like, there is, I think, research, not machine learning, that says that we use metaphors from what we know as humans. So there might be a very interesting question: how can we bring in information about these external metaphors, about like messages, for example? Messages meant something very different 100 years ago compared to now. How can we use this additional information to learn? But I don't think there is a solution to that problem, at least not yet, at least. But yeah, very interesting problem.
All right, so the next question is, it would be nice to have a discussion about how challenging it is to collaborate with companies in order to have access to real-world data for experimentation, since ML OSs may not express the real state of practice.
Yeah, I mean, I don't think there's a really easy answer to that. So in my experience, the best option is to actually go to the companies and work with them for a while. So I mean, I did this during a sabbatical, and that gave me access to lots of ideas and also data that I wouldn't have seen otherwise. At the same time, I wasn't too shocked about how software is developed in at least the company I joined. So it seems open source development is not that far away from what people in the industry are also doing.
I'm afraid that we need to wrap this up. So thank you all for being in this wonderful panel. Great answers. I'm going to be showing things to my student this year. So it was great having you, and well, I hope we'll meet each other physically for a change. Thank you.
Thank you.
Thank you.